Welcome to this presentation by the IET's Cambridge network. We represent members in the Cambridgeshire area, but we're very pleased tonight to welcome members from around the UK and indeed globally. My name is Phil Zerngast. I'm the chair of the local network and I'll be your host this evening. Before we start, I'd just like to mention that today is Purple Light Up Day. Purple Light Up is a global movement that champions disabled people and their economic contribution in the workforce. And the Cambridge Network and indeed the IET are very pleased and proud to support the aims of Purple Light Up. Now, a little bit of housekeeping before we get underway. We will be leaving questions to the end of the presentation, so if you do think of something, please use the Q&A button, which you'll find at the bottom of the screen if you wiggle the cursor over the Zoom control panel. We hope to answer all the questions tonight, but if we don't, our speakers offered to answer those offline and we will publish them later. We'll also be recording the event tonight, and that'll also be available later. I would encourage you to switch to speaker view to watch this presentation in this mode. Finally, I'll mention our next event, which is on the 21st of January on the subject of 5G. Now, on to our speaker tonight, and I'm very pleased to welcome Richard Prudence to speak. Richard Prudence is an electronic engineer who's currently working as a consultant with 42 Technology. 42 Technology is a technical consultancy based in Cambridge, which specializes in solving complex engineering problems and developing next generation products. Richard is currently technical lead on one of those projects, which is called Fusome, which is aimed at delivering the smart grid. So without further ado, I will hand over to Richard Prudence.
Thank you, Phil. I will share my screen now. So hopefully everyone can see the presentation. Yeah, so hello everyone, thank you for attending. I hope you're all doing well. And this evening I'd like to present to you some of the next generation solutions for the electrical grid that 42 Technology has been developing. So I'm going to just give a quick overview of what we'll cover tonight. Quick introduction to 42 Technology, just an explanation of who DNOs are and their responsibility in terms of the grid and distributing power, the thought behind the smart grid and why it's something we need and want, a quick glimpse into maximum demand indicators and where they're used, our solution as an alternative, which is Fusome as a substation meter, and some technical challenges that arose while we were doing some testing. And I have some data and some insights, which hopefully you'll find interesting. And then at the very end of the presentation, I'll look at some next steps as far as some technical development work I think we can still do. And the, yes, and then obviously the commercial end of where we hope this technology to go and what we hope it will enable. So 42 Technology is a product development and engineering consultancy. Our day-to-day work involves solving complex technical problems and developing next generation products. We do work cross-sector, and our clients come in various sizes, so they can be small startups that have just received their first round of venture capitalist funding or angel funding, through to large blue chip manufacturers that have businesses across the globe. But as far as the sectors that we work in regularly, consumer devices is a big one for us. Life sciences, delivering medical products and validating them to compliance. On the industrial and manufacturing side, we like to innovate and see whether or not we can optimize systems that exist already, automate new systems, and on the sustainability end, see whether we can reduce the energy that some existing processes might use. And in addition to that, it could be reduce water as part of a process as well. And that feeds into the confectionery side of things too. Energy is obviously a sector, and that's what today's presentation is about. But overall, if I were to sum us up, the point is to enhance the capabilities of an existing business and drive them towards better products as best as possible. So our experience is rather broad, given that we're playing in all these different sectors. But what we do most of the time is solve complex electromechanical systems, and that could be engineering new systems. But in general, it happens as a result of having a very competent electronics team, as well as a very competent mechanical team, and marrying the two together, you do end up creating new and exciting systems. Some of these systems, as we go through developments, involve creating new and bespoke sensors, of which I consider Fusome to be. But the other part of engineering, I think, is creating interactive products and making certain that whatever we do design is human-centered and simple to use and as intuitive as possible. I've put a list of clients up there just to give an idea of the scope of the various industries that we're in. But I mean, we have SAB Miller in the beer industry, Meggitt in aerospace, Atlas Genetics in medical. If you did want to have a look at a longer list of businesses and case studies, feel free to visit the website and see what we've been up to. So I will mention DNOs a few times throughout this presentation, so I wanted to just put something together to clarify who they are and what they do. In short, they are your energy suppliers. If you're calling in from the US or the EU, these are equivalent to the utilities. And what the DNOs do is they license the national grid hardware and an infrastructure that exists across the country in order to distribute and guarantee that you have power through your provider. In the UK, we have 6 DNOs that operate over 14 different regions. And I thought a good image that I found online was this, just to explain how they're divided up. If you wanted to know who your local DNO was, you could look this up through a postcode search. So I think something coming up and something that has been in development for some time now is the smart grid. So the national grid is making big strides to engage, well, to create the smart grid and all the sort of interlocking parts that make it up. But the central idea behind the smart grid is you do need digitization and you do need standardization of parts throughout the network. And again, the points that I've listed in front of you here now are about the key things we need to add to what we already have in order to get there. So something that's already been underway is adding support for mixed renewable sources. And these sources range from wind, solar, tidal. But in many ways, when you add these renewable resources to the network, they're still fairly localized. So you do have to manage how you use them and how you distribute power generated by them. Two-way communications between the DNOs and the DNOs, the infrastructure, and the national grid all needs to happen. There needs to be a complete loop of communication in order to make certain when decisions are made based on whether it's load shedding or load balancing, there's some idea of being able to map what the load is throughout the network. The output from having two-way communications is this idea of distribution intelligence. And this is about, in the long term, creating a control network, which means in the case of a failure, the network's able to fairly automatically self-route around fault locations and continue to provide households and businesses with power as needed. Real-time monitoring of loads is something that's happening that's been happening for some time. And in many ways, this is all about the smart meter roll-up with SMETS1 and SMETS2 meters, which has had mixed results, but it is happening. And the purpose of this is to gain some understanding of the day-to-day and yearly trends of how different districts and regions use power, so that you can manage and make better predictions of how to optimize the infrastructure that's in place already. Obviously, growing demand is a big topic. We're building ever more houses to support ever more people, and we have more and more electrical devices. And these electrical devices are more mixed than ever. So we're also in the middle of a transition to bringing more electric vehicles online, and we have to manage where that power is going to come from, and if we're going to use vehicles for energy transport as well. When it comes to another sort of output of having an optimized system with usable control systems and so on, you will get improved response times in the case of failures. And it should be automated enough that if a failure does occur, you can identify where it happened and a likely cause, and then therefore send out the appropriate engineers on a quick response time to make the necessary fix to get you back online. So I've titled this maximum demand indicators, but it's actually about the smart grid opportunity that we recognized. So through some earlier discussions with DNOs, we were made aware that DNOs are in the middle of a transition to DSOs, which is a digital system operator. And what that means is that they're now responsible for supporting some of the grid infrastructure that they use. At the moment, a lot of substations, of which there are 500,000 in the UK alone, they do by default have a very simple tool in order to measure what demand has happened in that substation. And it is a very simple analog meter. It's an analog ammeter, and what it does is every time you get a spike in demand, it moves the needle up, and it moves with it a small little plastic peg which it leaves in place, so you can see what the demand was at its peak at some given time. But what these really simple devices lack is the ability to provide any context for when and why this sudden spike in demand may have happened. It may have happened because feeders were switched in and out further up the network, or load was incorrectly put through the substation and then subsequently rerouted. But according to this, you'd have a maximum demand, and it would be the maximum apparent value, and it would consequently trigger decisions of investment of whether or not to upgrade that substation, to insert more feeders potentially, or to do away with the current substation and install something newer and fancier. So some substations, of course, do have some digital meters, and most of them make use of these Rogowski coils, which measure the magnetic field around around the live feeders, and therefore infer the current that's being driven through them. I think one of the big questions we had was, if there are digital meters and most substations don't have digital meters and we're relying on these maximum demand indicators, why are DNOs not taking the leap to digitize the grid as much as possible? And so what we did is we decided to have a quick deep dive into the market of the existing substation monitors. And what we uncovered was that on average, we were looking at around £2,000 per substation, which again, in the big picture of having 5,000 substations in total that you'd like to install something in, the prices get pretty astronomical. You can see why DNOs have not bit the bullet and gone for it. The other thing to appreciate while we were doing this research was that not all substations have the same number of feeders. So if you are going to spend 2,000 on a substation with many feeders, the economics stand up. But if you have a very few feeders and you want to install a substation monitor, it doesn't make any financial sense to do it. So The other thing that came out of the research we were looking at was that most of these substation monitors are quite time consuming to install. And part of the safety process of installing a Rogowski coil means the substations are powered down for a few minutes during the installation. Obviously, any downtime on the grid is unwanted, so having anything to avoid it is much better. Many of the existing substations are already equipped with advanced communication methods. They do support wireless communications, and this means that, yeah, DNOs wouldn't have to have their engineers drive out to the substations to perform the measurements, but it does lead them down a different route of paying subscriptions for data that's uploaded to the cloud, or being streamed onto their own service, but there's still that maintenance cost that remains ongoing despite having already spent the money on the meter and the engineer and the engineer's time to do the installation. We did get some feedback from them saying that retrofittable meters are the way to go. The Kelvatech model there is one of their go-tos because they're very quick to install. Their main feedback was they're very costly, and then they deviate from taking each substation away from standard components, which are these Schneider fuse handles and standard size fuses. So Fuse Ohm is 42's technology to the maximum demand indicator, and the plan was to make it into a maximum demand logger. So where does Fuse Ohm come from? So Fuse Ohm originates from a much smaller three-phase energy meter called Triple Ohm. The meter itself was a small internal venture to see whether we could come up with a smart meter design that completely avoided the need for current transformers. And we were looking for something that was invulnerable to magnetic fields, so that if in the case of electricity fraud, there are known cases of people holding large magnets over the current transformers to fool the smart meters to read out the incorrect data. So we were keen to come up with something that in the long term had fewer components, was lower cost to mass produce, and would stand the test of being used in developing nations. Version 2 of this particular technology was then a slight deviation, but our plan was to see what Triple Ohm could do as a development tool in a domestic setting. And the plan was to understand, by increasing the sampling frequency to 48 kilohertz, what we could understand of your household in the frequency domain, and in whether we could or couldn't find out how to disaggregate and pull out all the electrical items that you were using in your household. So the plan is pretty much like disaggregation, is similar to getting a phone bill for the energy usage that you used. So it'd be having an itemized list of what you've been using and how long you've been using it, and some idea of the total cost that it's costing you as a proportion of your energy bill. Now version 3, which is Triple Ohm, borrows some of the learnings from both version 1 and version 2, but it is going back to its roots as a three-phase meter, this time in a substation setting, but it's been designed from day one to be simple, very modular, low cost, and open to OEM features. The other thing which you can see from the image here is the core principle of how Triple Ohm operates is you have a shunt resistor through which you measure the current directly. You then have a galvanic isolation gap which sends data optically, and you have wireless power transfer through an air core transformer that's built into the PCB. And the intention here is, again, to make certain that whatever you're using on the sampling end is very well isolated from the metering end. Obviously keeping your mains voltage far away from your small 5 volt or 3.3 volt circuit that's performing calculations and data diagnostics. So Fuse Ohm was funded by Innovate UK under a first of a kind grant. Part one of this grant was to establish a clear business case using a novel technology that we'd developed. In our case, this was Triple Ohm. We began by just having very open discussions with DNOs to see whether they found this kind of opportunity of interest and whether they did in fact want to begin to migrate as many substations as possible into a more digital and more manageable form. So the proposal we came up with was to take Triple Ohm, adapt it, integrate it into these large fuse holders, and use the large fuse as a shunt in order to get away with reduced component counts. But in any case, the plan was to use our simple meter and reduce the cost per feeder to something more manageable for them to afford. The plan we put together included a thorough business plan on how we expected a rollout to happen. And we checked this with them to make certain that that is most likely how it would go about. But we collected some letters of support from these DNOs to then put forward as a part 2 recommendation to Innovate UK. So of the 5 of the 6 DNOs that we spoke to, all of them were interested in understanding load patterns of the grid. They made it very clear that having something safe and easy to install was a must. And if we could reduce that installation time to less than 3 minutes, it means there's a higher chance of being able to do installs without having to power the substation down. The system, once it was installed, had to be simple to operate, and wireless data, as I may have mentioned before, but wireless data was not universally designed between them. So as long as they were able to collect data and historic data on how these substations were being used, they were content with keeping their engineers doing the same tasks that they were, but of course having a lot more data to make the key decisions with. And again, we're back to this idea of retrofitability. They needed something that could cover a very wide range of their substations and use the most common components that they had at their disposal as well. So not to integrate anything new to bring about any further expense. So our proposal was Fuse Ohm, and I've put in an early image of how we thought the project would come together. But I think it's interesting because as we move through the next few slides, you'll see how it evolved. But there you can see it's very much about taking Triple Ohm as a circuit, that isolated PCB over there, and giving the engineers a readout display with some date and time to link to any peak current or average current that's being measured at the moment. So part 2 of the grant was the actual development plan of the project. The plan we put forward was a 12-month plan. I thought it was quite a good detailed plan that we constructed, but as happens with many projects, sometimes you have a bumpy start, and our bumpy start was a 3-month delay in the funds coming through. But despite that, the end date remained fixed. So we suddenly had ourselves on a really tight time-constrained project to deliver a huge amount of testing. The plan itself went through your standard design, build, and test. Testing as always throws up a few hiccups, which are always exciting. But the one thing we did as part of the trial we put together is we worked very closely with PNDC. So PNDC is the Power Network Demonstration Centre in Glasgow through the University of Strathclyde. And part of giving DNO's confidence in the device and the proposal we had was demonstrating the thorough testing that we would undertake to get it there and to compare it to existing meters. So it wasn't a matter of creating something innovative and seeing whether it was usable. It was very much to have something to validate it against and confirm that it was easy to install, and the readings were, of course, within a certain expected tolerance as well. We will get to the results from this study at the very end of the presentation. So my original plan before COVID was to do a live demonstration of this installation. But for now, I'm going to pass over to a video we made earlier with a colleague doing the installation of fuse ohm on a fuse gear.
Introducing Fuse Ohm, an innovative new three-phase monitoring system for electricity substations. Plug-and-play upgrading of existing fuseways in minutes, enabling smart asset management and fault analysis. The patent-pending system uses adapters that simply plug in between the existing fuseways and fuse holders. Data is transferred to the interface module for local display, logging, and external connectivity. Designed for retrofitting to typical UK substation components. The simple installation can be done in minutes, reducing labour costs and avoiding extended customer outages. Provides a true fit and forget system that avoids the need for any external wiring or separate power supply, unlike typical monitoring systems installed today. Prototype systems have been trialled in the Power Networks Demonstration Centre. Future interface module variants are planned with alternate connectivity and display options, and a low-profile version with custom fuse holders for tight installs. We are also exploring wider applications for the technology. Get in touch for further information or to learn more about our wider expertise in electronics and sensor technologies.
So hopefully you enjoyed that. I'll dive into some of the detailed parts of what makes up fuse ohm and how we went about building our prototype. So most of what this prototype is three identical adapters, which we've had to, we'd spent some time at the very beginning as part of our requirements, speccing out how we wanted these adapters to fit together. Daisy chaining seemed like an obvious go-to solution for it, but we had to plan ahead of time so as not to create a system where we would then feed an AC reference voltage down to the main controller. So we actually had to spread much of the electronics between them. So we do have a three-phase bridge rectifier circuit separated into three different parts between each of them. And what it meant was that all of these could be identical and there was no given order for these adapters to be installed. So there's not adapter 1, adapter 2, adapter 3. They can go in any sequence. We made certain also to ensure that existing fuse holders were fully supported, and that if DNOs and the substations they were using already had particular handles, that again they wouldn't have any need to change them. The control box, as we'll get to, is quite a nice modular and open part of the design. It does mean that if there are any other features that a particular substation needs over another, we can make variants fairly quickly for different communication protocols and mesh it into existing systems if they already exist. So when it comes to the data logging, the good thing about fuse ohm as opposed to the maximum demand indicator or any Rogowski coil-based measurement is that we are able to measure voltage and we can also infer the exact phase angle for each of the phases. And as part of that, it means we do have true power measurement. The other thing that we've taken from the other Triple Ohm project, the Triple Ohm HF, is this concept of having a high frequency window, which we'd call like an audio recording, where you could sample the data at a much higher data rate and only log log more intermittently. But it means that for fault analysis, there's the potential for understanding what may have been the cause and giving some idea of diagnostics in the lead up to the failure that you may have experienced. So this is something we're researching at the moment. Again, the display was a natural readout for what's happening. You get instantaneous readings as well as historic. And yes, we place it at the bottom just because that's where there is the most space, and we didn't want to conflict with any other meters that might be present near the top of the substation. I have, more for completeness, put in a prototype adapter cross-section here, but it gives you some idea of how components clip together and the various pieces that you couldn't see from the video. There is, of course, a small PCB that lives in the center performing all the data logging, and there is a later step on miniaturizing this to accommodate for a wider range of different fuseways. You'll see also that we do have some very common features that exist between the actual fuse handles and our adapters. And due to the time constraints we were under, we made certain to use the already compliant parts from fuse handles that we could salvage at the time. The control box, I thought was a nice way of presenting information to any engineer that had to do an assessment of a substation. But we still kept in mind the key focus of having the maximum demand indicator being the improvement point. And in the same way, you'd sort of walk up to these substations, take note of what was read on the dial, and then reset it. We wanted the dynamic to be, you turn up at the substation, remove the SD card, since the last time it was logged, put in a new blank memory card, and then take the data back to base for processing and understanding. I've also put in a quick transparency of the control box. And the idea here is just you can see how these ribbon cables interlock and how the pieces connect together. You'll see also that there's a fair amount of space in that controller for additional wireless modules should you need them for your particular application. As far as future communications, we're more than happy to make changes to the controller as it is and support different ones. Ethernet, I should have added Wi-Fi, but there's 2G, 4G, 5G, NB-IoT I think will become a popular choice. And SCADA, of course, is, I think, most likely a go-to solution for integrating Fuse-Ohm into the grid management system once we eventually get there. So PNDC was kind of the ultimate trial of how Fuse-Ohm would survive and be used in real life in a real substation. But ahead of that, we took the action to prepare some additional tests. And what we did is using some parts that we've put together, we created our own custom phantom load as a representative substation to do some practical three-phase high current tests and three-phase voltage tests. And we had some decent discoveries of it. The aim was, of course, to test it from a thermal standpoint, giving it a constant current of 100 amps, and see if there were any magnetic shielding issues that we had to accommodate before the trial. So just a quick jump into some of the key challenges we had once we built that test rig. So the shunt resistors we're dealing with in Fuse-Ohm are very large. They're a giant piece of copper, and this giant piece of copper changes its resistance with temperature. And without knowing it, we'd found another variable that we hadn't considered from the beginning. So we had to start logging temperature of this shunt resistor throughout any of the tests we were doing. The other thing that came to our surprise, I think, was how strong the magnetic fields were when you were delivering 600 odd amps through these pieces of metal. And we thought initially that, the standard rule of twisted pairs on either side would be enough to cancel it. But no matter what we did, we couldn't rectify it. The final rectification was not twisted pairs. It was adding a very customized trace along the outside of these shunt resistors. And we had to make certain on either side of this trace that we put in, it would cancel out the magnetic interference that was happening on it. And once we understood what was happening, we managed to get some very clear readings. And the smallest reading that we were able to get was, I think, 10 nanoamps. So it was very tiny. And it meant we had a huge dynamic range at the end of it. Fuse connections surprisingly posed an issue given the size of the shunt resistors we were using. So if you connected these very large fuses in at a slight angle, or not quite forced in properly, we actually noticed that there's a measurable voltage drop along the shunt resistor. So it would suddenly read a much higher resistance than if it was a perfect connection. So recognizing the problem, we made certain that on the display, we could display a quick alert to installers to say they'd not installed the fuse appropriately. So in a way, we managed to turn what was quite a bad discovery into something good, and it meant that installations became quite straightforward. I mentioned again, just it wasn't much of a problem, but it's more of a design consideration from early on, but we wanted all connectors to be identical. And to do that, we were distributing circuits, as I mentioned, between all of the adapter boards. So just onto PNDC and some of the data that we were collecting there and how the installation went. So once at PNDC, FuseOhm was fairly quick to install. After handing over some instructions to their engineer, they managed to do it within 3 minutes, and the system booted up as we wanted, showing the correct voltage. And we then decided to put it through a long load test of a constant 400 amps for a number of hours, and this was to check real outdoor inner cabinet thermal testing, just to see whether anything would come up before we engaged in the full 3-day trial to test them to destruction if we could. So the later tests were, of course, these robustness tests that I was mentioning, and they're all about inducing pre-programmed faults so that we can see incredible voltage spikes, some current spikes, some erratic behavior, and look at how it recovered from these over voltage and high current conditions. The trials overall demonstrated very good current and voltage accuracy, which is what we were hoping for. The tests took all 3 days, and thankfully all of the adapters that we took with us, I think we took 9 of them with us, all came back and they'd all survived. The conclusion from what we'd put forward was that as a result of the testing, we proved that the response very closely matches that of a Fluke L2 meter, which is one of the industry standards for doing short-term testing in these substation environments. Off the back of showing those results to Western Power Distribution, they were more than happy to support us in undertaking a 12-month trial. And so I'll go through some of these results that we collected and some of the raw data you expect from a real substation. So the field trial, we had collected a fairly decent amount of data on the SD card, which we would routinely go and take data off. We had modified the controller board on FuseOhm to support Wi-Fi, which meant that we didn't have to have the engineers open the cabinet all the time. We could walk nearby, log in, and then take the readings off. In the data, what we noticed was there was a sudden drop in overall current. I remember when this happened, there was a bit of a worry or a concern that maybe something we'd done as far as the programming of the controller had gone wrong, but we had in fact captured a real moment that WPD had switched out a feeder from that particular substation. And we phoned them up and confirmed that they had in fact done this on the 17th of February at midnight. Of course, the nice realization of this is that if we were to rely on what the maximum demand indicator in the substation was stating, it would state the maximum of somewhere between 80 to 200 amps. And of course, the new reading, based on what we were looking at, is actually nearer 40. So yeah, just goes to show that we designed something and it has fulfilled its purpose quite well. We gathered some decent insights, which have led to a few questions of what else could we do with Fusome, given that it is very sensitive. And part of that was analyzing the regular cycles in power usage. And one thing that WPD had recommended was maybe it makes sense to consider a remote alarm system or a notification system, so that in the case of remote workers who live nearby to these substations, that notifications could be given out at the appropriate time to inform them. We also had some, without our 10 Hertz sampling rate, we were able to capture the moment that some erratic loads further downstream of the substation had something go wrong. Again, we're not certain what that might have been about, but it was nice to see that we can capture them. WPD gave us a good quote confirming most of our efforts, and the Fusome units were installed, operating, and collecting real-time data within one of our substations, literally within minutes. So I think it was a nice pat on the back that the team had been looking for. And it was nice to see that a DNO had the genuine feedback that matched what PNDC had given us. So what have we achieved with Fusome? We've developed something that's extremely simple and fast to install. It's around a 3-minute installation. We've made use of the Triple Ohm IP to see whether we could create a more modular system that takes full capabilities of the underlying patents. We've significantly reduced the price per feeder for a meter, and now we're looking at around 200 once it gets into bulk production after another iteration of development. The target use case for this is still small substations, but we hope to see a rollout at some point where they are deployed. We've managed to do a testing at PNDC and on the grid to validate that it works and it's safe and it's reliable, and we've had good feedback from it. We're beginning to get interest from suppliers, people that want to adopt it and make alterations to it. We of course admit that there are some future enhancements that we should be making, and some of that is around the sort of core IP as well. There's more consideration to be had for how the shunt was designed and how we should do it in the future, and all of that's being fed into the version 2. And I think looking at it in general, we realized that while we had wanted to design just a maximum demand logger, it does have the potential to be so much more. So just a quick thing on next steps. I hadn't really gone through the costs very much until now, so I thought it'd be good to throw this in. But the existing prototype design that we had at a 10K production rate is more or less £300, which is still significantly below if some of these other solutions were used. The revised design we've optimized and we're trying to get it down further. But at this point, it's around about 150 to 200 pounds per feeder. And that again assumes a 100K plus production rate. Again, assuming that we could try and get this into an actual rollout position. Our aims are to see Fusome in as many secondary substations as possible. We'd also like to, on the technical end, as I said, improve the shunt design. I think since it is such a core feature of what we've developed, it'd be a shame not to do the final improvements to it. there's some miniaturization on the on the sampling board that lives in the adapter that could be done. And what this means is we should be able to integrate and accommodate for much smaller fuse holders as well. So I realize we've picked the largest one as part of this demonstration, but that's a good starting point to have. And then of course there's enhancing features in the way of fault detection and recording predictive maintenance actions onto the SD card as well, or again, wireless. But there's also this thought that maybe we should be looking at earth faults and some other tools that the engineers at DNOs do need to be aware of. So it'd be good to discuss these with them. On the commercial end, we are a consultancy. We're not a product manufacturer, and we don't have the intention to manufacture it ourselves. But we are looking to get OEMs in the area active and involved with us to make use of what we've constructed and improve on it as well. We're more than happy to discuss more trials. We're happy to consider these trials abroad as well. And in the case of people who have private grids, we'd be more than happy to speak with you on something more widespread. When it comes to recommendations on what other people think we could do with it, we're also happy to make changes to the design we have and see what else we could get from it. Yes, thank you very much. And if you have any questions after this, feel free to message me or send me an email. And likewise, if you have some very specific commercialization questions, please feel free to contact my colleague, Russell Hagar. Thank you very much.
Thank you, Richard. Well, we've got plenty of questions. So I will hand you over to my colleague, David Blake, who will take you through those. Thank you.
Right. Thank you very much, Phil. And thank you, Richard. I'm sure we can put together some of these good questions. I have to apologize. I have a few technical problems myself. So if I look strange in a picture, I am strange, but it's probably a bit stranger still with the lighting arrangements. First question was metering Rogowski coils. Could this be open-ended and wrapped around feeders without interrupting supplies? And why have DNOs not used this approach?
So DNOs are using the approach, and many of the large meters that you can buy for substations accommodate, as I say, like up to 16 and some of them even 28 different Rogowski coils. So the benefit is that a Rogowski coil is quite cheap and they are easy to install, but the current procedures that you would need to install them does require the substation to be powered down. And if you are going to power it down and install 16 of them, that's a fair amount of downtime.
Yeah, okay. Does the fuse ohm offer single shot fault re-energization and distance to fault technology similar to Calvatech and EA technology? Or is fuse ohm purely a data logger?
At the moment, fuse ohm is a data logger, and these kinds of features are what we're hoping to add in future generations of it.
Okay. How does the adapter tighten onto the fuse gear jaw?
Through the same, it's the same mechanical sort of interlock that you have for locking the fuse onto the fuseway. So it's exactly the same mechanism, but
Okay.
you tighten the screw, and that screw will bolt, will apply a force onto the fuse.
So it uses sort of existing infrastructure and away it goes.
Yes, yeah.
Yeah, okay. How is it planned to analyze the data produced? Is there any software? Are you going to provide any software at all?
For now, we've been running our own MATLAB scripts on the data to provide the outputs, but I imagine if there were a rollout and again having some standardization over what it would produce would be useful. Yeah, I think in the future that's definitely within scope. Okay.
One comment really, it's strange that DNOs have not invested in digital meters. It's thought they will pay for themselves. Have you got any views on that?
I think, yeah, well, I think they do pay for themselves. I think it's a matter of you do have to make the decision of where you're installing it. If you are going to install some of them and they perhaps rely on wireless features and the location you want to double check is a very remote system and you don't have any access to 3G or whatever the wireless feature that might be integrated, then again, you're paying for features that you might not need. So what the stance with FuseOhm was start with the bare basics and enable the DNOs to make the decisions based on the digital data that they collect slowly.
Okay. In fact, that moves on to another question, which is, why is wireless data not desired? Surely that goes in the face of the smart meter concept in domestic installations. And if the DNOs cannot easily obtain the data, won't it be neglected and not used?
So, yeah, it's a good question. I think the key thing is knowing and justifying why you're going to make further investments in an area of a grid. So if you have some data supporting it to say that on average over the last 3 years, the thing that's most harming this substation's life is that we keep switching things through it and that it doesn't live a very sort of stable life, then you might make the decision to upgrade it to something more permanent or something that supports higher demand. But yes, having wireless does mean that you have that circular feedback happening between the management system and where the energy is going. But it's an additional thing to manage as well. It is an additional cost. And I think they just made us very aware that at least if they're going to do a mass rollout, they can't be supporting however many gigs of data all of these substations will be generating all at once. You really have to take it slow and then justify how you're going to streamline that as a process. Okay.
Moving on again to sort of data issues, does the sampling rate mean how many snapshots per second you are reading? What would be the purpose of going to the kilohertz area?
So on the kilohertz area, we wanted to find, again, this wasn't implemented in FuseOhm, but this was part of our Triple Ohm HF meter. But having harmonic data means that you have more information to distinguish different appliances with. So you could tell quite easily whether it was, say, a hairdryer or a vacuum cleaner, and you could tell those two apart. I mean, the sensitivity we had on Triple Ohm HF meant that we could tell the difference between a vacuum cleaner that was running and was getting full versus a vacuum cleaner that was empty and had just started up. So it leads you down the route of predictive maintenance, and we think that there is some potential there for that kind of thinking on the grid as well.
Okay. If there's a fault situation, can the fuse melt? And if so, would it be costly to replace the units when damaged under a fuse operation?
I don't think the fuses can melt, but they are normally quite slow blow. So yeah, they do heat up substantially, but I don't think there'd be any melting or anything like that.
Okay.
But they can easily be replaced. That's the whole point of having a fuse handle, yeah.
Okay. Was the development funded under the Network Innovation Allowance by any chance? And if so, is there a reference code available?
I believe it was. I will find the code. Just feel free to message me and I'll find it.
Okay. And just to interrupt there, if anybody wants a CPD certificate or to make contact and you haven't got Richard's direct email address, you can always email things to cambsec@gmx.com, or you can look up the IET Cambridge website and you'll find contact details actually on there. If we move on, it's a question about retrofitting to existing switchgear. Are the manufacturers on board as there are possible warranty issues with connecting into their switchgear?
So we've not opened direct discussions with them to see if they could integrate it, but I think that's the kind of discussion we would have. It would be more, would they want to integrate FuseOhm directly into their fuse gear as a feature? rather than yeah, keep it as a bolt-on.
Okay. How does the device affect LV board testing? E.g., conducting a ladder test requires access to the LV phase bars. Does this block that happening? Or can you sort of, do you have to remove the device, your fuse ohm device, or is there another way around this?
Just like a standard substation, you just remove the fuse handle and the fuse.
Okay. And somebody's asking here, I know it was said that it could be used with SCADA in future. Does this mean real-time capabilities instead of the data storage method of data acquisition?
Yes, yeah. The controller board that we clip on at the very bottom of fuse ohm is intended to be adaptable, and if SCADA was the desired adaptation that that was wanted or desired, we'd be more than happy to fit it out with those features.
Okay. How do you calibrate for first installation and for change of fuse cartridge?
So from what I remember, while you're busy installing it, we take some initial measurements of the resistance, and this gives some indication of whether you've installed it properly. But no, there's no real calibration step.
Okay.
We've already pre-programmed them with the relevant data.
Good. Comment here, brilliant presentation. And how is the meter measuring the current as they cannot see a CT within the unit?
So one of the two bars of metal that live in the adapter, which is an extension of the bus bar, is used as a very large shunt resistor. And yes, we have two terminals on that bus bar that are fed down to the meter board, and that meter board will of course be monitoring the voltage across it.
Okay. Progress looks promising, but for 500,000 substations, an automated fault detection, identification and reporting mechanism is needed to avoid a data tsunami. Is WPD intended to support this development?
No, for now they've been facilitating how we do those tests to make certain that what we have designed is sufficient as a meter, nothing more.
Okay. Getting near to the end now, how do you see these systems interacting with vehicle to grid, smart grid for real-time changes?
I think that's some time away. But I think given that we can see daily trends with the device, certainly this idea of alerting users and alerting system owners to slow increases in power usage. If everyone were to adopt, say, electric vehicles down one street, I think, yeah, there'd probably be a way of notifying and scheduling when a particular street should begin their charge cycle, something like that.
Okay. What is the fault rating of the device?
I think it's 20 kilovolts.
Okay. So that's quite a high capability.
Yes.
Yeah. And are there any considerations to provide support for Modbus RTU to facilitate the transfer of the measurements to the control center through a substation RTU?
Yes, we are looking into this at the moment, but I mean, if that individual has some specific questions, I'd be more than happy to take it up with them as well.
Okay. Well, you've got another praise here. Good and very informative presentation. Is there a chance of getting a copy of it? Well, we will be putting the presentation in the next few days on the IET Cambridge website. And a recording of this particular presentation will become available potentially on the YouTube system, which we're sort of putting together at the moment. And we'll announce that on our Cambridge IET website. Where you are installing your new equipment, is it for indoor service only? If outdoors, is condensation a problem that has to be addressed in some way?
So the PNDC tests were done in mid-December. And again, we have warm bus bars and snow and all this kind of stuff. We didn't have any issues with condensation.
Okay. Well, here's a positive suggestion. Has this been presented to Network Rail? Because it would seem that this also has the application for monitoring overhead line equipment for electric trains.
It hasn't in this form, but yeah, I think it's something to revisit, definitely.
Okay. Have you thought about continuous high frequency recording for power quality and harmonic distortion analysis, a growing issue?
Yes, we have, the device already has support for higher sampling rates, but just as a logger, the focus was on making certain that it as a unit was functional and useful, and so we turned some of those features down, but it does support much higher sampling frequencies.
Okay. A little comment here was, any reason why one DNO was left out and only 5 were contacted?
We were under very tight time constraints with part 1 as well. So it was the end of November, and we had to very quickly coordinate with all of them to get their feedback, and we missed one off. Just due to Christmas holidays.
Okay. Installation involves removing the existing fuses from the fuse board. Does this mean that power is cut off to the consumers, the customers supplied by the circuit?
Yes, for a very short period, yeah, just a few seconds.
Okay. And does this measure power in one direction only?
I believe at the moment it does, but I should double check whether we've added any other additional features, so I can get back to that person as well if they want to.
Okay. Can you go into more detail on the control board? Does it use off-the-shelf components? In other words, I think how maintainable is it, and how many iterations did it take to create?
I think we managed to do this in 2 iterations. It does have it uses fairly standard components, and yeah, I don't think there's anything very bespoke about it, except for the connectors that we've used in throughout the daisy chaining setup that we've set up.
Yes. Have I missed something? But doesn't your device measure the voltage drop across the fuse cartridge? So how sure are you that of the resistance?
No, so our first concept when we put the business plan together was to make use of the fuse as a shunt resistor, but there's far too much variation between each of those fuses, so we didn't go down that route, and the solution to that was to extend the bus bar. So hence the way the adapters have sort of come to be.
Okay. The penultimate question, how do you power the electronics?
So we use a 3-phase bridge rectifier, which is cut into pieces and distributed between those 3 adapters. So a normal 3-phase bridge rectifier will have 6 diodes, and since we have 3 adapter boards, we've now put 2 diodes into each of those adapter boards, so that we have a high voltage low line and a high voltage high line as a DC reference point for all the electronics to be powered off of.
Okay, so a few more questions come in if we've got time. What's the maximum voltage that the system measures using the standard fuse mount? I think you said earlier on there's a safety limit of 20 kV.
Yeah, and it'll be around there.
Okay. Have you had any problems with harmonics?
So we are aware that there is an issue with skin effect that we've become aware of, which will influence what the resistance of the shunt is at different frequencies. But this is something that we can accommodate for with the appropriate maths on the device. So it's not really a problem we see. It's it's taken care of, but not developed into this final product or this prototype.
Okay. And is resistance measured by 4-terminal method?
No, because all of the shunt pieces that we're using are all machined, we do know the resistance between those 2 points, and we do measure them before we install the adapter boards.
Okay, well, that's it, Richard. Thank you very much. I think I'll leave Phil to take over, but just to tell everybody that I've got lots and lots of requests here for CPD certificates, which I'll email out tomorrow.
Have we
I'm not
lost
doing it
David
this
there?
evening. Sorry?
I think so. Perhaps his IT problems have finally caught up with him tonight.
Yeah. I was just saying, Phil, that I'll send out CPD certificates tomorrow.
Great. Good. In that case, Richard, just leaves me to say thank you very much for your presentation and sharing your development journey with Fusome. It's clearly what could be potentially an important part of what would be a multifaceted solution to actually creating a genuine smart grid. So that was very interesting. Okay.
Thank you.
So thank you all for your time and joining us on this this presentation. Please keep an eye out for our future events, which you can find by looking, searching for the IET Cambridge network. Please remember to register in advance to make sure of a place. So that concludes tonight's event. So on behalf of the IET Cambridge network, I'd like to say thank you all for joining. I wish you all a peaceful and healthy season, festive season, and hopefully we'll see you again next year. Thank you very much, and you can all disconnect now. Thank you.
Cheers.
Thank you.
Yeah, bye.
Good night.